Let's begin. So, left off a couple examples last time. We tried them. Test 2 will be a lot more challenging than it has to be if you didn't try this over the weekend, so hopefully you didn't just wait on me here. Because I have a lot more examples I want to get through, so I'm going to get through this relatively quickly. We did A, B, C, D last time, so what'd you do here? Anyone do this one? Yeah?
1 over cosine squared is equal to secant squared.
Okay, integral of secant squared.
Then you can take out the 3, and then secant squared, once you go through it, it'll just be tan.
And so fundamental theorem of calculus, you plug in the top number minus plug in the bottom number. Tangent of pi over 3. It's radical 3, and then we have 3. And tangent of 0? 0. It's 0. That's how you do that one. Or you do this one. Yep.
Sine squared x in this case, sine squared x can be written as 1.
Just one. So antiderivative of 1 is just x between 0 and 13. Plug into 13 minus plug into 0. 13. How do you do this one? Yeah.
So you can separate, you get like a separated fraction, so it'll be square root of x minus square root of y.
Right, so that's going to go into that square root of x times. How do you anti-differentiate square root of x?
You can use the power rule thing. for-
How does that apply?
So the square root of x can be written as x to 1/2. So you would add 1 to each. And then that creates 3 times x.
So you add 1 to the power, get 3 over 2, divide by the new power, divide by a fraction, same as multiplying by its reciprocal. Here, you add 1 to the power, you get a half, divide by the new power, means multiply by the reciprocal. That's between 1 and 4. So, I will plug in 4, 2/3 times 4 to the 3/2 minus 6 times 4 to the 1/2. Plug in the 4, 2/3 times 4 to the 3/2 minus plug in. Minus, now you're going to plug in the bottom number, 2/3 times 1 4 to the 3 halves. It's 8, because that's the square root of 4 cubed. Square root of 4 is 2, cube that you get 8, so this is 16 over 3. Here, the square root of 4 is 2 times 6, that's 12. And here we have minus 2/3 plus 6. So we have 16/3 minus 2/3, that's 14/3 minus 6. Greater common denominator here. So that's 14 minus 18 over 6. Not over 3. Minus 4 over 3. And last time we looked at what it meant to have like a negative sign here. And yes, we generally think of it as area, but based on how our integrals were defined, if your curve dips below the x-axis, it will actually have a negative area. And so that just means this guy dips below the x-axis at certain points. And the part that's below the x-axis is actually larger than the part, if any, that's above the x-axis. That's G. I do want to mention something about that though. Common error. Okay, so in the previous integral, x minus 3 over the square root of x dx, you cannot integrate the top and bottom separately. So what I don't want you to do, highly illegal, you do it, I just give you 0 and I move on with my life. You cannot just go into the top and apply the rules. Oh, let's do a power rule here and a power rule there. And then let's go to the denominator and do a power rule there. And then that's the answer. You know? So it's going to be x squared over 2 minus 3x divided by x to the 3 over 2 times 2/3. Very, very wrong. Super wrong. Not paying attention at all. You cannot actually do that individually. I mean, something like that cannot even work with derivatives, right? Like if you have a fraction, a rational function, and you want to find a derivative, you need a whole quotient rule. You need a whole procedure to actually go through that. In general, integrals are more difficult than derivatives. If you have a rule that a derivative can't deal with very easily, an integral is not going to be able to deal with it very easily. So it's very important that you realize that you can't just go and take integral of pieces and stick them together. It doesn't actually work. Integration has rules, kind of like product rule, working rule, chain rule, etc. So you just have to be aware of that. What you do want to do is you try to simplify something first so that you can use a rule that you're thinking of. But don't think you can integrate things in pieces. The only way you can integrate things in pieces, as I mentioned last time, was with the sum. Right? If things are separated by pluses or minuses, you can integrate each piece that's separated by pluses or minuses. But within a single term, you can't just integrate parts of it and stick it together. Actually, it doesn't work. It's very wrong. So just be aware of that. And of course, that being said, how do we do this one? Right? So you can't just integrate this part and integrate that part and then stick it together, right? It's not going to be x squared over 2 times x squared over 2 minus 2x. That would be very wrong. Because, let's think of it, if we were taking derivatives, we couldn't do that. We couldn't do it with each piece. Integrals are going to actually be worse. So what you do here is you expand. And Now you can apply the rule. This looks like the power rule. It's an x to the n. X cubed over 3. And this would be x squared. And you plug in the 4, 4 cubed over 3 minus 4 squared. Minus, you plug in 0, that one's going to just be 0. So 4 cubed is what? And 16 times 3? That's 48, 64 minus 48. 16 over 3. So when things start getting complicated, you have to figure out a way to simplify them first to look like one of the basic rules we had before. Let's do this one. Let's just power rule. This one's actually not that bad. The point of me giving you this example is for me to show you something else. What are you going to get here?
0.
You'll get 0 because you plug in the 1 minus, you plug in the negative 1, the fourth power is going to make it a positive 1, and you get 0, which is kind of strange. They're under that curve 0. What's actually happening here? X cubed looks like this. So remember, when our graph is underneath the x-axis, our integral formula will return negative values. So from 1, the area under our integral is going to measure the area under here, but then when it goes down to minus 1, it'll actually measure the area under here. And the thing about x cubed is it's symmetric about the origin. So it turns out that this area and that area are exactly the same magnitude, and so they kind of cancel each other out. Which gives us another helpful tip. Is odd. Remember what it means for a function to be odd, i.e. f of minus x equals the negative of f of x. So something like x cubed is odd, sine of x is odd, etc. Then, integral from minus a to a of f of x will be 0 all the time. You never actually have to figure it out. Once you can recognize something is odd. So, every now and then you'll see examples like this, where they give you an integral that is, for all intents and purposes, literally impossible to actually integrate. So you like x e to the x squared plus cosine of x to the fourth over, say, x secant x, like something really crazy like that. And they'll go over here, say something like minus pi to pi, or something to try to confuse you. And the trick for something like that is to know it's actually 0, because it's an odd function. If I plug in all my x is equal negative x into that function, I get the negative of that function. And so this is actually a very helpful thing. So how we make that statement, how we express this idea, we say the following. The integral of an odd function on we call this a balanced interval. I mentioned that last time as well, just to remind you. Is 0. Balanced interval. Once you're going from a negative number to a positive number, it's non-zero. Negative number to a positive number. If you realize that your function is odd, the answer is going to give you 0. You don't have to actually calculate it. So that is to add to a lot of other useful things that I told you last time. So let me quickly remind you of those because they're actually important. Well, not important. They make your life a lot easier. So there are times when a problem might seem very difficult, and it's not as difficult as you might think because you have all these shortcuts all over the place that you can figure out. Recall from last time. If f is even, then if you integrate that on the balanced interval, it's going to be double the answer from half on half the interval. So if your f of minus x is equal to f of x, it doesn't actually make a difference, like y equals x squared or y equals cosine of x. That is going to be true. You should also recall, so that's, you should also recall, like I said, if curve is under x-axis, definite integral will be negative for that portion. Another thing I mentioned is if you're integrating, say, sine of x or cosine of x on any interval that is a multiple of their period. So you start at a part a and you go up to a part like a plus 2n pi plus or minus. Then those would also give you 0. Right, so you integrate sine and cosine on an interval that is a multiple of their period. So you're integrating from like 0 to 2 pi, or 1 pi to 3 pi, right? Or pi to 11 pi, or something like that. All of those will actually give you 0. And that will help you out in later classes where you might end up with a situation where you're getting things like say this goes from 0 to 2 pi up. So you could be working on a problem, you went through hell to derive this, and eventually you end up here to do an integral, and now you're like, oh my god, now I have to do this long integral. But it turns out that you don't have to do a long integral, because how you tend to look at this is you look at this as sine squared times cosine. You look at this as, say, cosine squared times sine of x. With a technique I'm about to teach you later, you'll realize that the integral of this is going to be like sine cubed over 3. The integral of that is going to be cosine cubed over 3. Those both have periods on 0 to 2 pi where they dip below and above. And so these will give you 0. This will give you 0 because the actual, where's that theta? Sorry with x's and went into theta. give you 0 because his period is pi, and we're on a multiple of that period. For this guy, you'd realize that, well, you'd use the half angle formula. That's 1/2 minus 1/2 cosine 2 theta. This will give you 0. So you can start with a very intimidating integral, and it's just actually the integral of a half. Right? But you can just look at that and know that that's what it's going to be. And so this, knowing this is super useful, super. I mean, you could survive without it, but your life would be a lot harder. Right? It's not going to be long before you get like really difficult problems to do. I mean, top 2 and top 3. Differential equations, forget about it. That's just, yeah. So knowing these little tricks here can actually help you out a lot. Let's move on to example 2. I think those are all the tips I gave you last time. Just remember all of those. Let's see. Okay. Find d prime. What's g prime? Yeah?
Sounds good.
That's it. That's the derivative. So it's the fundamental theorem of calculus, part 2. By the way, this is something that might cause some confusion unless, it'll take a few seconds to clear it up, but it might cause some confusion. The way I taught you the fundamental theorem of calculus, what I did first and did that at part 1, and then I used that to prove part 2. It turns out that you could actually go the other way. It's possible to prove the part 2 first and then prove the part 1. And so what you will find is that there will be, it's not really a discrepancy, but there will be a discrepancy in which part someone might call part 1 versus part 2. So there will be cases where what I call part 1, someone else would call part 2, or what I call part 2, someone else would call part 1. So just be aware of that. So what we think of as the second fundamental theorem of calculus, a lot of other people would think of as the first fundamental theorem of calculus. And so if someone ever says, oh, we're using the first fundamental theorem of calculus, and you know that they're doing this, oh, that's why you're okay, yeah, they learned it the other way around. To me, it was easier to prove part 1 the way I did it and then use that in part 2 as opposed to doing this and then proving part 1. So that's how we did it. But the part 2 and part 1 is not set in stone. Different textbooks will think of different things, do it in different orders. But you can use either one and prove the other. So that's just something you should be aware of. But the fundamental theorem of calculus part 1, part 2 for us says that d dx, be careful how you write these, of an integral from a constant to x of f of t dt is just equal to f of x. You just plug in the x. The derivative cancels out the integrals. What about this one? How'd you guys do that one? You want to do that one?
Or just 2.
Yeah, exactly.
Negative cosine x cubed minus
Where did the negative come from?
because normally we did it, the constant is at the bottom and
Yeah.
the x is at the top.
Right.
Now we are doing it the other way, so the integral of that would be some constant minus the integral of that cosine thing. So the derivative would be negative.
Well, this is, I guess you can take this as helpful fact number 4, 5, I don't know. But a negative would come into play here because the integral from a to b of f of x dx is equal to the negative of b to a of f of x dx. Now, that's something that's helpful fact, and that's something that is true, and that's something that you could make sense of geometrically, but you'll kind of have to twist your brain in a knot for a little bit. But it turns out with the fundamental theorem of calculus, that's actually not hard to show. If I have a to b of f of x dx, this is going to be big F of b minus big F of a. What I could do is I could just factor out a negative. That would look like big F of a minus big F of b. And by the fundamental theorem of calculus, remember that the guy that goes first is the guy that's on the top limit. The guy that goes last is the guy that's on the bottom limit. Second is factor out a negative, and what it ends up doing is it switches the position of b and a in the right side of the fundamental theorem part 1, which means it will actually negate the original one. So if you have an integral and you would probably care about the order being switched on the limits, you can actually do that at any given time. You just have to put a negative sign there. This follows from the fundamental theorem of calculus. It's easy to see. So when you are looking at the fundamental theorem of calculus part 2, it's very important that you notice the constant is on the bottom. Remember, your formulas are templates, meaning if something doesn't look exactly like the situation or things are in exactly the positions that they are in the formula, you cannot apply the formula until you finagle it to make it look like that position. With this question, the constant is in the top, which means as of this moment, this does not apply because the constant is in the bottom. So how we can do it is we can switch these to get the constant in the bottom, and switching these just negates the original integral. So I can actually think of this as the negative of, put 4 down here, x up there. And now I can differentiate. The negative sign is not going to matter because I'm taking a derivative, it's just going to hang out. And the derivative of an integral in this form is just going to be, you take the x and plug it in. So that's another helpful tip. You can swap the limits on an integral at will as long as you put in a negative sign. Pronounce that a little more. So that's how we would deal with part B. Part C. Just throwing a P in there because I want you to get used to the fact that it can be any variable, just not the variable that's in the limits. I do deal with this one. So, by the way, this I should have said, we call it G, so this is G prime. So that was our G. So g is equal to this, which equals that. G prime is equal to this. How do we deal with this one? Yeah?
The f prime and the x squared times t to the t plus x to the 6.
Yeah. Chain rule is how we deal with it. Notice here, in this case, we do have a constant on the bottom, but we do not have x on top. We have some other function on top. And we knew from our derivative rules, if you replace x with some function, how you actually deal with that situation is the chain rule. So we're going to take derivatives the way we normally do, which means we are going to plug in the thing in the top. But that thing isn't just an x, so what do? You multiply by the derivative. So that would give you 3x squared times the cube root of 2 plus x to the 6. And that is this answer. So, another pro tip. Number 5, maybe 6. I wasn't counting. You can generalize the fundamental theorem of calculus part 2. Part 2, meaning you could take the derivative of some function that doesn't go up to x, but rather to some other function. Let's call it g of x. In this case, our g of x was x cubed. How do you take the derivative of something where you know a rule that has x in a certain position, but now x gets replaced with some other function? The chain rule is how you do it. So you go and you plug that guy in just like usual, but you'd actually multiply by the derivative of the inside. So you can generalize the second fundamental theorem of calculus that way. And that would yield this answer. Now the final example. The ones that I've seen on past finals are kind of like example C or D, usually example D. So let's make sure we know how to deal with that one, because they're not going to ask you one that's so straightforward. They'll ask you one where not only do you need to use the second fundamental theorem of calculus, you have to actually manipulate it a little bit before actually using it. So let's finish up with D. You want to find P prime. How do you go about finding P prime? Yeah, Montero?
Well, you know that sine t over t is just 1.
No, we don't know that. That's in fact not true. Huh? What was he missing?
The limit is t approaches 0. Oh, yeah.
Right. Sine t over t is 1 if there's a limit in front of here setting t go to 0. Sine t over t by itself is not 1. Okay. So, ideas? Yeah, is that good?
It was a similar approach to Jhevon. So d prime would be sine of x cubed over x cubed times 3x squared minus sine of x squared plus 1 over x squared plus 1 times 2x.
Well, I saw you using a similar approach in the first part of that, but where did the minus come from?
Oh, minus the bottom. big F of the top minus the big F of the bottom.
Yeah, but we're not integrating, we're differentiating.
Yeah, but then if you differentiate that, it's going to be the same thing, right? So, yeah, right.
What do you want to say here?
The integral of that thing is going to be big T of
Integral of what?
whatever that thing is.
Whatever this thing is, okay?
It's going to be big F of X. Whatever.
What are the
A and B.
A and B?
So that's going to be T minus A. And then we take a derivative. Did take a derivative of both sides.
Okay, but that would actually give you 0 on this side.
So since A and B is not constant, so if A and B is some function, then it's not 0.
So you don't want A and B then, you want some other functions
Yeah.
here. Like it's G of X and H of X. Or some other variable. So you put them in here. H of T, G of T. Well, technically you have to multiply by a derivative. I mean, I see where you're going with here, but you're going to have to finesse that a little bit more here. Because you're going to have to multiply by an H prime, and then you have to wonder, well, what's going to happen to the H prime and the G prime? Here's another way to look at it, which is helpful tip number 6 or 7. I should have numbered these guys. If you have the integral from A to B of f of x dx, it turns out you can do the following. In most cases, as long as your function is still continuous on the interval and all that good stuff, you can actually throw in a middleman. So I can say this is integral from A to C of f of x dx plus the integral from C to B of f of x dx. So f is continuous, blah, blah, blah. Right? So I can take an integral from A to B, and I can split it into two integrals where I put someone else, start at A, go up to C, then go from C to B. It's the same as going from A directly to B. One way you can see why that is true, well, fundamental of calculus again. You have A to B of f of x dx. That is big F of B minus big F of A. We can cheat in that way that math people love to do, and we can do something like subtract F of C, add F of C. And this part here, by the fundamental theorem of calculus, is integral from C to B of f of x dx, plus this guy right here, by the fundamental theorem of calculus, is the integral from A to C of f of x dx. Another way you can see this is graphically. Let's say we have our function doing this thing here. Here is A, here is B. I care about this area. But one thing I could do is I could pick an intermediate point C, and I could measure the area from A up to C, and then measure the area from C up to B, And if I add those two areas together, I get the whole area that I had before, right? And the area over here, this area is going to be given by the integral from A to C. And this is going to be given by the integral from C to B. And to find the total area from A to B, I just add them together. So if I add them together, that is the total area from A to B. So we can do that. How does that help us here? Well, to bring it back to the point, the problem we wanted to solve, we can split this into two parts. I can go x squared plus 1 up to some constant, let's say 1, just because of sine of t, where t is t. Plus, now go from 1 up to x cubed of sine of t over t dt. And you could in fact put any constant you want here, so let's put a c, just any constant where our function is going to behave and we don't have anything crazy going on. So we could do that. We know how to do with this. When the top is a function that's not x, we just do the chain rule. Here, the function is actually on the bottom, but we also know how to deal with that. That's actually going to be negative, and I can flip these guys. So you can split an integral in two parts, putting in an intermediate guide. That's valid as long as your function works on the intervals that you're splitting it up on. Or at least works on each individual piece, the way you're splitting it up. And now you just apply the rule to each part. Kind of feel weird putting the negative in front, so I'll just put this part in front. Don't get confused. So I'm going to plug in the x cubed over the x cubed, and I multiply by the derivative because I have to use a chain rule. Minus sine of x squared plus 1 over x squared plus 1 multiplied by the derivative of the inside. So this is going to be, well, this can cancel to that. It's going to be 3 sine of x cubed over x minus 2x sine of x squared plus 1 over x squared plus 1. And how do we simplify this? You cancel the x's here, right? No, you cannot do that. It's canceling across sums. Do that again. Can we cancel these x's here? No, you cannot do that. You cannot go inside the angle of a trig function and cancel with something outside. So that's the answer. Do not go any further and do anything silly. It's not going to be fair for you to do all this hard work and then you do something silly right here and back. Nope, forget it, 0. So that is how we compute definite integrals and how we can take derivatives of definite integrals when our limits are variable. Hopefully you worked through those on over the weekend. I actually want to move on now to a new technique that's going to help us find antiderivatives in more complicated situations. So let's do that. So remember last time, was the last time, maybe the time before, I told you about the basic rules of integration, right? These are the rules that we got by reversing derivative rules, as well as just knowing how to find the antiderivative of individual functions, right? So there was the integral of x to the n, there was the integral of 1 over x, there was the integral of sine x, and the integral of cosine x. All these guys are just things that we knew right away because we have derivative rules that describe them. We also have, we have those basic rules. It's how do we find the antiderivatives of individual functions that we know how to differentiate. And sometimes things can get a little bit more complicated as they did in our examples here, but what we can do is we can like simplify, we can split the fraction into two parts, or we can multiply things out and to get recover the basic rules that way. But it turns out sometimes you do not have that option. So I'm going to teach you one technique that allows you to get around when you can't do that, and you will learn a bunch of other techniques in Calc 2. So let's actually start with a new technique here, a technique that's going to help us find antiderivatives / integrals of more complicated functions that we can't really simplify with algebra beforehand. And again, remember, finding antiderivatives is an important endeavor. It can help us solve problems that we couldn't have solved before. It also has many applications, which I'll probably mention a couple. But the next, I forgot what it was. I think this is 5.5. It doesn't matter. The title is going to be Integration by Substitution. Which is going to be the lowest level of sophisticated integral techniques that you know. So we're going to give you, I'm going to give you a technique that will allow you to find the antiderivatives of complicated functions, i.e. functions that don't look like a basic rule. You will learn many more techniques in Calc 2. What is integration by substitution? It is the reverse of the chain rule. Okay? So just like how we can reverse individual formulas, we can reverse entire methods. And integration by substitution is how we reverse the chain rule. Basically, it says, if you want to find the integral of something that looks like the following, then the answer must be the following. Which isn't very helpful. Like, I mean, yes, I know if you differentiate this, you will get an expression that looks like that by the chain rule, but you just telling me that in reverse isn't really helpful, is it? I mean, I can add in one step here that says, okay, what we could do is we could substitute something for the g of x. Okay? Let's say I can substitute the variable u. So if I say u equals g of x, I want you to notice that if I differentiate that, find du dx, that would be g prime of x. Which means I can write my du as g prime of x dx. And so what that actually transforms this integral into is it would now look like the integral of f prime of u du. And by the second fundamental theorem of calculus, I know that the integral of a derivative is just the original function. That is going to be f of u, of course, plus a constant. And that's this side. So what I did just now is I just described to you the process of integration by substitution. But let's actually make this a little bit more foolproof. Okay. So You're on a test, you're on a quiz, some random integral pops up. Compute this, find the value of this. Integrate this function, right? What do you do? Okay, so always step one will be try to apply a basic rule. Always. That's always what you're going to try to do first. Meaning, does the integral of x to the n work? X to the n plus 1 over x n plus 1 plus c. Or does the antiderivative of 1 over x works? ln of absolute value of x plus c, etc. Right? The basic rules, right? That's what you're going to try to apply first. This thing I'm looking at, can I use a basic rule to do it? If you can, just do it. And if not, you move on to something else. 2. Try to simplify to use a basic rule. Okay? We saw examples like that. So an example like x minus 2 all over radical x is such an example, right? Now that by itself does not look like a basic rule, but I could divide the radical x into each part, separate them, and then each individual would look like that rule, right? So I could just like, okay, let's simplify this, let's factor, let's cancel stuff, let's move things around, let's bring things up, write the radical as a power, bring it up, get a negative power. You can do algebraic manipulation to simplify to a basic rule. Now, if that doesn't work, it turns out that the third thing you will try is substitution. And even when you go to Calc 2 and higher, substitution will always be the third thing you try. It's always going to be the third thing. Right? Now, you are going to have other things that you have to do, etc. But you're going to learn about those in Calc 2 and later. Right? But number 3 is always substitution. I'm looking at an integral. Does a basic rule apply? No. Can I simplify it to get a basic rule? No. Substitution is the next thing you're going to think about. Right? So there's a process for looking at integrals, just like how there's a process for looking at limits. We'll try to plug in first. No. Simplify to plug in. No. Okay. Special technique. Does the graph work? Right. So you're going to have like a whole strategy for approaching integrals because they are complicated, to say the least. So you are faced with a random one. It's not going to be obvious what rule or what integration technique is going to work. Far less obvious than it is for derivatives. So you want to kind of have a strategy in mind. And when you're doing a random integral, this is always the first 3 things you try. Substitution is always right up there at number 3. So if you now know that, okay, what I'm looking at, I cannot use a basic rule, I cannot simplify to use a basic rule, I'm thinking substitution is what I'm going to want to go with. How do I actually get this process to work? Let's actually talk about that. Step 1 in the substitution process. With a single variable, you're going to replace some expression in your integrand that makes it very complicated, right? Chances are that's going to be the thing that doesn't allow you to simplify, and you're going to replace it with a single variable because that is always going to, you're going to try to make it a simpler situation. By replacing with a single variable, say u, right? U is customarily used, traditional to use u as a variable that's being substituted. So much so to the point that some students will call this technique U substitution, but that's a bad idea. Do not call it U substitution. There are going to be cases where you want to substitute variables other than U for very specific reasons. Because probably technique number 4 that you're going to learn is going to be integration by parts, and there's a U in the formula for integration by parts. So you don't want to mix up your U's. So don't think of it as U substitution. So just think of it as I'm going to substitute U as long as I know in the future I'm not going to need to do something like integration by parts or something else, or my U doesn't mean anything. So we're going to separate substitute, that's replace, aka substitute. We're going to substitute a complicating expression for a single variable, U. This will make the function, this should make the integrand simple. Where simpler here is a very specific definition. Looks like a basic rule. Okay. It does look like a basic rule. I'm going to want to make it look like a basic rule by substituting a particular variable. Now, 2. There are 2 things that you need to have happen to make it work. 1, the substitution should make the integrand simpler. I have seen students substitute things that actually make their lives more complicated. I've also seen students substitute things like U equals X. It's always a bad substitution. That's never going to be a good idea, ever, right? So like if you have like the integral of x squared dx, and then you say U equals X, what do you think that's going to do? It's literally going to just rewrite the exact same integral in a different variable. It doesn't make the situation any better, right? U equals X, never a good substitution. Don't even think about it. I don't know why people do it, but I've seen it happen a lot. I've also seen people substitute things and it doesn't simplify anything. It actually makes it harder. The first thing you want to do is make it easier, make it simpler. Substitute something that's going to make it easier. So that's the first thing, which you would think would be obvious, but it's actually not obvious. I have to mention it. 2, the second thing, and this is more important, computation speaking, the derivative of the expression you substitute must be a factor elsewhere. In the integrand. Now, that's all you need for Calc 1. Always works in Calc 1. When you get to Calc 2 or higher, no longer works, the life is complicated, you're big kids now, you should be able to deal with another situation, but you don't really need to worry about this in Calc 1 class. Or, right, so the substitution should make the thing simpler, and the derivative of the expression that you substitute should be elsewhere in the integrand. I should also mention here, constant factors don't matter. Constant factor off is okay. So don't worry about that. So if you find a derivative and it's like 3x squared, and in your integrand it's 7x squared, that's okay. The fact that there's a 3 versus a 7, a constant factor doesn't matter because for derivatives you can factor them out. Or You're gonna have examples in Calc 2 where you won't see the derivative right away, but you can somehow replace the other variables using the u and the du that you chose. Example, you want to integrate e to the square root of x. It's going to require a technique like that. We won't learn how to do that. You learn that in Calc 2. So, looks like a simple function, but it's actually not so simple to. Well, in the grand scheme of things, it's very simple, but for Calc 1, it's not a simple thing to do. Substitution is probably how you would start that, but a direct substitution isn't going to work because part 1 is not going to work out for 3. Okay, so I know I want to use substitution. I'm going to replace the complicated expression with a variable, say u. The substitution must achieve 2 things. I am going to find du, meaning I'm going to differentiate the u expression, and plug in all the u expressions. And replace all instances of the original variable. So let's say I give you an integral of f of x dx. X is your original variable. Once your substitution is through, there should be no x's anywhere, right? Including in the dx part, by the way. So you shouldn't have a dx left over, there should be no x's left over. Once you say u equals blah, you need to get to a point where the integral you're looking at has only u's in it, has no x's. You're literally changing the variable. That's something you talk about in Calc 3, change your variable. It's actually a bigger thing than what we're doing here. So you literally want to change it into a new variable called u, and that brings us to step 4. The new integral in u should look like a basic rule. Apply it. Integrate. Step 5. So you're going to have a new integral and a new variable. You're going to be able to apply a basic rule or simplify so that you can apply a basic rule. And you're going to just do the rule. You're going to integrate it. What you're going to realize is the answer that you get will have u in the answer, usually, right? So because your original variable wasn't u, you kind of have to put it back. So 5 you want to back substitute. So you're going to put back, you're going to replace all the u's in your answer with the original expression that you originally took out, back substitute to get answer in original variable. Now, this step is optional if you have a definite integral, and I'll probably talk about that a little bit. Now, so if you have numbers on your integral sign, it's optional whether you want to go back to the original variable or not, but you'd have to actually change the limits. We'll do some examples on that, but it's optional. And I would go as far as to say, in Calc 2, you're going to learn a technique called trig substitution. If you have a definite integral where you have to use trig substitution, I would always change the limits and not back substitute. Remember my words. Remember that, right? You're in Calc 2. Your professor comes in and says, "Hi kids, today we're going to do trig substitution." You're going to if he gives us a definite integral and not back substitute. That should be in your head, right? Because swapping back to the original variable isn't always as easy as you would think. For trigonometric substitution, it could be a lot of work. But that's the integration by substitution. It's a 5-step process. Looks quite complicated by me explaining it, but it just takes a long time to write down in English what we're doing. But that's how you're going to do it. Let me show you an example. Look at that integral. Now, that integral pops up on a test. First thing you're going to think, does that look like a basic rule? You will quickly find out it does not. The second thing you're going to think, can I simplify that to look like a basic rule? And here's what a bunch of people would try. Oh, I can. So that's actually just x plus 2. And I can do that, and then I'd multiply this out. And then I could do the power rule. And I would promptly give you 0 and move on with my life. Because you cannot distribute a radical across a sum. You cannot distribute powers across a sum. You do something like that, I ignore everything you write. I just go down to the bottom, write 0, and move on. I'm not even going to read it. I'm not wasting my time. You cannot do that. So, can't simplify that way. Can you simplify it any other way? I mean, there are ways to expand radicals, but you'll need literally an infinite number of terms to do that. You learned about that in Calc 2. So, can't do that. So here's something, it doesn't look like a basic rule, and I can't, with my basic laws of algebra, actually simplify it to look like a basic rule. Once you realize you're in that situation, now you're going to be like, substitution. Substitution is what I'm going to have to do. And in Calculus 1, that will always be the answer. Beyond Calculus 1, that's not always the answer, but in Calculus 1, it's always the answer. If a basic rule doesn't work and I can't simplify it to look like a basic rule, substitution. It's always substitution. So, now you're going to look at this and you're going to like, what do I substitute? Right? I want to use a variable, say u, to substitute an expression. What is making this complicated? Well, not just the radical. The radical itself doesn't make it complicated, right? The inside, the expression under the radical, that makes it complicated. Because if this was just an x, what would have happened? Well, that's just x to the half. Multiply by this and use the power rule, right? So what makes this complicated is the thing under the radical. Makes it complicated. It prevents you from simplifying, so what you would do is u equals this guy. That's going to be your first step. So you're going to look at this. Can I use a basic rule? No. Can I simplify to look like a basic rule? No. Okay. Why can't I simplify? What's in my way? Who is making things complicated? That guy. Okay, get rid of him. Right? Set him to be a single variable, because if you have a single variable under your radical, that's easy to deal with. That's power rule stuff. Okay? So now your goal is to transform this integral into the variable u. Now, in order to do that, you're going to have to change every instance of x, including the dx, by the way. Right? So, how do you get rid of that? Well, you're going to do your derivatives at this point. You're going to find the du. The derivative of that is going to be 2x dx. Now remember, you just find du dx and multiply both sides by dx. The Leibniz notation can do that. So that is going to be your derivative. And now what you realize is that you see here x dx. And you see here x dx. The derivative I just found, I see it's a factor somewhere else in my integrand. Right? Now, again, this says 2, that says 5. I don't care. I don't care about the fact that it's all 5 constant. I can factor that 5 out. In fact, I can divide both sides by 2 here and factor the 2 off. So, how I would have done it back when I was a little Jhevon, I would just divide by the 2 and solve for the expression that I want, but for some reason, students, that confuses a lot of students. So I normally tell them, you can proceed many ways here, but I guess the easiest way is to just solve for the dx. I normally just tell people, solve for the dx, don't worry about it. So that's going to be your du over 2x. Now, if you of course, you can divide 3 by 2 and then swap in half du for x dx. I will be fine with that. That's how I would have done it. But from my experience, most students like this way. And they make less mistakes by doing that. So solve for the dx. Now what you're going to do is you're going to substitute everything. I am going to take u, so take this expression, replace it with u, and I'm going to take this expression and replace the dx. Now, the 5x, I didn't do anything with it, but this guy is just u, and my dx is now du over 2x. Now what you notice is going to happen, the x's cancel, which is why I needed the derivative to be there, so that I can cancel it out. Now, what do I do with the 5 and the 2? It's a constant, factor it out in front. And that looks easier. Not only is that easier, but I can use a basic rule. What is the basic rule here? Right, power rule. That's just u to the 1/2. So I'm going to, that is, add 1 to the power, I get 3/2, divide by the new power, 2/3, plus c. So this here now gives us 5 over 3 u to the 3/2 plus c. And that's the answer, that's the integral, that's the antiderivative. However, the answer comes to us in a variable u. The original question was asked in the variable x. So I need to reinterpret this answer in terms of my original variable. All you have to do is, this is what's called back substituting. I'm going to just go in and replace my u with the original thing that I replaced it with in the first place. And that is actually the answer. And you can check, if you differentiate this, you will get that. Right, the 3 over 2 is going to come down, the 3's are going to cancel, I'm going to have 5 over 2, subtract 1 from this, I'm going to get the radical, and then multiply by the inside, I would get 2x, the 2's would then cancel, and I would have this left over. So, we just found the antiderivative like that. Right? Not a basic rule, doesn't look like a basic rule, can't simplify it, looks like a basic rule. Substitution, calc 1, always the answer. Find something that is complicated, use a single variable to represent it, differentiate that expression, make sure that the derivative, the variable part of the derivative, is somewhere else in the function. If you're off by a constant factor, it's not going to matter because you can always factor the constants out. It should give you an integral that is now easier. Easier in what sense? There's a basic rule that fits this situation. Or I can now use algebra to get a basic rule that fits that situation. And then just apply the rule. You'll get an answer u, swap it back. This is called integration by substitution. Let's do some examples. And again, one of those things you have to do a bunch of examples. To get used to it. At this point, it's too far back to remember. I don't know if it's me or maybe my professor just couldn't teach it very well, but I remember the first time I saw something, I was totally confused. I literally had to just teach myself through problems. And then I said, oh, yeah, all right, okay. And then what you're going to realize is there's going to come a point where you're going to be praying for a substitution. You're going to, please God, give me an integration by substitution, because all the other techniques will be so complicated. Substitution is going to be like, oh yeah, that thing we learned at the end of Calc 1. It's like kindergarten. Okay, let's do some examples. So if you're a little confused in the beginning, don't worry. Practice will save you. And so we're going to do tons of examples. And of course, whatever I don't get through, you need to get through. There's also something else I want to show you.
Percent.
You don't always need to substitute a single variable. Sometimes you can substitute an expression that just makes it easier. In fact, that's kind of the idea that trig substitution is based on. So, going back to the previous example, which I forgot, it's 5x squared of x squared plus 4. Now, I realize after I do a substitution here, I'm going to end up with a radical, which gives me a half power, which by itself isn't that bad. But if I have a bunch of radicals all over the place, that can get quickly annoying. So what I can do is instead make a substitution such that while it goes into the radical, it will actually get rid of the radical. This is actually something that you can actually do. So I could say, for example, set u squared to be the inside. Right? Or saying u equals the square root of that is the same idea. Use the whole thing. So I say u squared is equal to that. What you can do is just like usual, just differentiate both sides. 2u du equals 2x dx. You cancel the 2's. And so you get u du equals x dx. What you can then do is, let's say, solve for the dx. That would be u du over x. And then you plug in. Now what you're going to realize happens here, 5x times, well, the square root of u squared. And my dx is going to be u du over x. The x's would cancel, the square root and the square would cancel out, and I just actually end up with 5u squared du, right? Which is nicer than the other one. Like I don't have to deal with a fraction. I can integrate that 5u cubed over 3 plus c, and then I replace u with what it is, well, which is in fact x squared minus x squared plus 4 to the 1/2. So this is 5 times x squared plus 4 to the 1/2 cubed. And notice that that's the same answer. So you can get a little bit creative with your substitutions. There's no reason why you have to substitute a single variable. In fact, in Calc 2, you'll learn this idea in trig substitution at the very minimum. Where you see an expression like this, you might want to substitute something like x equals 2 tangent theta or something like that. Don't worry about it, that's Calc 2. Let's go through a few of these.
If that confuses you, don't worry about it, just do it the way I said before.
That only saves you time and mild annoyance. It's not gonna like make or break you. So, I see that. Does it look like a basic rule? No. The basic rule says the integral of sine x is minus cosine x plus c. So that doesn't look like a basic rule. Can I simplify it to look like a basic rule? Well, no. What am I going to do? Move the x inside here. First of all, can't do that. Second of all, it's impossible to integrate sine of x cubed. We don't have an answer for that. So that won't help either. So what I'm saying, what's making this complicated? Well, that x squared inside the sine is pretty annoying. Set u equals x squared. Du d2x dx. Solve for dx. And plug in. X's will cancel. The 2 here factors out and becomes a half. And what do you know? That looks like a basic rule. The integral of that is minus cosine of u. back substitute because that was my u. So now I'm going to put back the x squared minus 1/2 cosine of x squared plus c. And that's your answer. And you can differentiate that. You'll see that you get the original. You'll get x sine of x squared. B. Look at that. That was complicated. Can I use a basic rule? No. Can I simplify to use a basic rule? No. So I'm going to do substitution. Always the answer in Calc 1. What makes this complicated? That diamond radical is pretty complicated. Oh, is this a good substitution? I don't know. Let me check. Here's an x squared. There's an x squared. Then you go and you plug it in. Then you solve for the dx. And you plug everyone in. So this is 2x squared times that will just become radical u. And your dx will become du over 3x squared. The x squared will cancel. And you would end up with 2/3 the integral of u to the 1/2 du. That would equal to, well, u to the 3/2 times 2/3, so it's 4/9 plus c. And that's the answer. I just swapped it back. Look at this. That looks complicated. Maybe I can rewrite it to look like a basic rule. We can do that. Still looks complicated. Can we simplify it any further, Jim? No, we can't, Jhevon. So, the guy like this. Johnson, can't do it, Captain. What do? What makes this complicated? Well, there's a guy inside of a radical that's a sum. So I would set u equals that guy. Probably a good idea. du is going to be minus 1 dx. Well, that's a constant factor, so that definitely doesn't affect anything. We're good. This means that my dx can be minus 1 times du. And I can just swap that in. So this will be u to the 1/2. Well, minus 1/2 times minus 1 du. Well, that's just negative u to the minus 1/2 du. And I can do the power rule. Add 1 to the power. You get 1/2, divide by the new power, you get 2, so that's minus 2 u plus c. So this is minus 2 u 4 minus x to the 1/2 plus c. And you can differentiate that and see that you'll get that. Let's do another one. D. Oh, that one looks complicated. Okay, so you look at that. Does it look like a basic rule? No. Can we simplify it to look like a basic rule? No. What makes it complicated? Well, that guy in the square is pretty annoying. I mean, this guy can come up with x to the minus 1/2, but even if I move this guy out, he's still going to give us a problem. Set u equals that guy. Our du is going to be, well, 1 over 2 radical x dx. solve for dx. Right? Notice that here I have the 1 over x dx, and notice over here I have the 1 over radical x dx. So, good substitution. So we plug this in now. So I have this 1 over radical x, didn't do anything with that. This one I changed to u, so that's u squared. My dx becomes this, 2 radical x du. The radical x's will cancel. I can factor out a 2 and bring this u up. That's my integral. That looks pretty basic. Add 1 to the power, divide by the new power. That's that answer. Now, eventually you'll be doing these, and you'll start to get bored after a while, kind of like how I'm getting bored right now. And that's when you know you've studied enough. See, the moment you're still kind of thinking about it, you didn't do enough problems. You need to find another textbook to do more problems. So, of course, the trick here is to be able to spot the complicating expression pretty quickly, so you can just get rid of it. Now, I do have the option here of doing a u cubed substitution, but let's keep it simple. Doesn't look like a basic rule. Can I simplify it to look like a basic rule? No. What's making it complicated? That guy u equals this guy. Okay. How do I know that's a good substitution? Well, differentiate it. Do you see that guy somewhere else? Oh, you mean the x dx? Yeah, I see it somewhere else. Good substitution. Solve for the dx. Plug in. X didn't do anything with. This guy I made a u. My dx would become du over 2x. The x's are going to cancel. This 2 I can factor out, it's a constant. This I can bring up and write it as a power. This is u to the minus 1/3. Add 1 to the power, you get 2/3. Divide by the new power, you get 3/2. So here I get 3 over 4. I'm going to replace the u with the thing I plugged into the original, 3 plus x squared. So the 2/3 plus c. That's the answer. You can differentiate that and check that that would be the answer. If I head to H. We'll wrap up with this example. You guys try the others on your own. What do you substitute? Well, firstly, does it look like a basic rule? No. Simplify it to look like a basic rule? No. Okay. Substitution is going to be the answer. What do we substitute? I'm going to show you how to actually change the limits afterwards as well.
Likewise.
Yeah, but then you'd still have an ln of u, right? You know what that is? Huh? We don't know what that is. You're learning Calc 2 how to find the antiderivative of ln. At the moment, we don't know. So getting rid of the radical x actually doesn't make our lives easier. I would get something that's just as complicated for a Calc 1 person. We don't know how to integrate ln. We know how to differentiate ln, we get 1 over x, but we don't know how to anti-differentiate. Not yet. But, I mean, technically there's a 1 over x here. And also technically, radical x is x to the half, and the log rule will say I can bring powers down in front. So that's what I'm looking at. Now what's complicated? The ln is complicated. Not the radical, the ln is what's complicated. I don't know how to integrate an ln. U equals ln x. du 1 over x dx. And I have that guy right here. So, this would be, I will have 1/2 u over x times, here I'm going to solve for dx, that's equal to x du. X is cancelled. I have 1/2 u du. Now, what I want you to realize here is that, yes, I have it in a new variable u, but the original limits were in terms of a variable x. So I cannot plug these x's into the u's. So to remind myself of that, I keep writing the x here. So say, oh, that's an x value, that's an x value, that's an x value. Don't plug it into the u, that's an x value. Okay. U squared over 2 between x equals 1 up to e. Now, how do you actually deal with this fundamental theorem of calculus? Well, if your limits are an x, you just back substitute before plugging them in. So this is ln of x between 1 and e. This is 1/2. E here, ln of e is 1, so that's just 1/2. Minus ln of 1, 0. So 1/2 is it. You did have an option of changing the limits. And this is what I mean by back substitution is optional when you have a definite interval. So let's say I had this same guy, 1 to e, 1/2 ln of x over x. I could do my u equals ln, my du is equal to 1 over x dx, so my dx equals dx du. But then I could change limits. So I want the limits to go from x to u's. How do I do that? Well, you can use the same substitution equation to change the limits. So here you can say, well, when x equals 1, our u would be ln of 1, because u is ln of the x. So that's going to be 0. And then when x equals e, our u is going to be ln of e, which is 1. So now you can go in and you can not only plug in the x's and replace them with u's, you can actually replace the limits themselves. This will be the limit from 0 to 1 of 1/2 u du, right? I can get the same way. So now, integrate that, u squared over 2, u squared over 4 here. Oh, which I think we missed that before. So 1/2 times 1/2, it should be over 4. But now I don't have to actually change the change it back to x's because I changed my limits to be in the new variable u. So I can just take this 1, plug in, that's a quarter. Take the 0, plug in, that's 0. So this is what I mean. The back substitution option is optional if you have definite integrals. And in fact, when you're in Calc 2 and you're doing something like trig substitution, I would literally always do it this way. You always change the limits for anything more complicated than a regular substitution because sometimes actually changing back to the original variable is difficult. So we will stop there. So you have your test on Wednesday. The reviews are up. Make sure, and the solutions, make sure you use them responsibly. I have a little bit more to talk about, so we will actually have a lecture for the last part of Wednesday's class. So your test is going to be 1 hour long, and in the last 40 minutes I'll mention some applications. And I think there might be one other problem type you want to get to do, but aside from this, we're pretty much done with the syllabus. I will see you guys on Wednesday.